Hey everyone, and welcome to another video. It's been a while. In this video, we're going to be looking at the basics of the new unit we're in, which is electricity. Electricity is a huge topic. I mean, people literally become electrical engineers, so you can go in depth in so many different aspects of it, but we're going to focus on just a couple basic concepts today, in the hopes of getting you up to speed on how to do one of the most important things, which is circuit analysis, and I'll explain what that is as well. We're going to start with a very important concept though, and that concept is called Kirchhoff's law. Kirchhoff's law. And technically there's actually two Kirchhoff's laws. There's Kirchhoff's current law, and there's Kirchhoff's voltage law. So we are going to look at current law and voltage law and explain what they are. So Kirchhoff's current law is stated like this. The sum of current that enters a junction is equal to the sum of the current that exits the junction. Well, first of all, what's a junction? Well, here's a junction. A junction is just any point in a circuit where multiple wires intersect and there's multiple paths that the electricity can take. So here the electricity has like different paths that they can take from here, and so this is a junction. What is not a junction? This isn't a junction. It's just a corner. There's only one path electricity can take. So Kirchhoff's current law, which is often abbreviated to literally just Kirchhoff's current law, is basically this law that deals with junctions. And I'll draw just a really simple circuit. This is a battery. Here is a junction, you can see. And then there's going to be a resistor here. And there's going to be, sure, a resistor here. Why not? The whole point of this is that there's this junction here. I'm going to zoom in on. Kirchhoff's current law says that the sum of the current that enters this junction is going to be equal to the sum of the current that exits it. So into this junction, we're getting one source of current. That's coming from this battery. The current is going like this, like this, like this, and is going into the junction. One source of current. Coming out of the junction, we have two new paths of current. Current can go through this load, or it can come around here and go through this load. And what Kirchhoff's current law says is that the sum of the current that enters it, so the green line, is going to have to equal the current that exits it, so the red line. If we give these all symbols, let's call this I in, because it's the current in. And this can be I out 1, because it's the first path out, and I out 2, because it's the second path out. Then Kirchhoff's current law tells us that I in is going to equal I out 1 and I out 2. And this applies to any scenario where you have a junction. Where you have a junction, we always remember that the current path in, the sum of that current is going to be the same as the sum of the current path out. Here's another junction that's kind of different. I'm not going to draw the whole circuit this time. This is a junction. This time there are two paths into it and only one path out. And again, the two inputs would have to equal the output. Very simple law, pretty much self-explanatory. That's Kirchhoff's current law. The other half of Kirchhoff's law is Kirchhoff's voltage law. And Kirchhoff's voltage law is stated like this. The sum of the potential difference, which is another word for voltage, around any circuit loop is equal to 0. So this one's maybe a little less intuitive to think about when we say, okay, the sum of the potential difference around any circuit loop is equal to 0, but it'll make sense once I show you. So here's another circuit. This one is literally just going to be a loop. Here's our circuit, and current goes around conventionally like this. And Kirchhoff's voltage law is basically telling us that the sum of the potential difference around this entire thing is going to be 0. And that's a little unintuitive to explain because potential difference is a difference. It is the difference between one place and another place in the circuit. So all this is really saying is that if I start with a certain amount of voltage potential difference across this battery, let's say there's a voltmeter here and it's measuring the voltage, that this voltage, basically what it's saying, isn't going anywhere. This circuit is going to, when all is said and done, this loop is not going to lose any of this voltage. The difference between before and after is going to be 0. Basically, if this is the source and this is the first and second loads, we can say that the voltage at the source equals V1 plus V2. Basically, we don't lose voltage. Voltage doesn't disappear. These are Kirchhoff's current laws and voltage laws. And they're kind of useful in the way that they're stated, but really what they're stating are kind of just more or less obvious truths. Where they come in handy is they allow us to come to the conclusion of these very important equations for different types of circuits. And there are equations that deal with voltage, current, and resistance for series circuits and parallel circuits. These are the more important things, so I'm going to explain them in more detail. Here is the series side, and here is the parallel side. So, what is a series circuit? What is a parallel circuit? To be pretty straightforward, series circuits have things lined up, one after another, end to end. This is a series circuit. These two resistors, R1 and R2, are in series, which means that they are connected end to end. One end to the other end, to the other end, to the other end. Parallel circuits have things that are going side by side, not end to end, for instance, like this. An important characteristic of a parallel circuit is that it has junctions, these things that we talked about over here. Parallel circuits have multiple paths for electricity to travel. A series circuit has only one path. Here, the current can only go this way. Here, the current could either go this way or this way. There's both paths available to it. So that's the difference between a series and a parallel circuit, which is really important. Most circuits are neither series nor parallel. They're a combination of the two. For instance, if you took this simple series circuit, but now R1 was two resistors in parallel, you now have a more complex circuit, which is a combination of series and parallel. When we get these circuits, the most important thing is to break them down into component parts. And I'm going to talk more about that when I get to the section on circuit analysis. For now, we're going to deal with these formulas for series and parallel circuits. There are, once again, equations for voltage, current, and resistance. And there is a pattern, in a way, which is basically that one of them is kind of opposite to the other. And you'll see what I mean. Let's look at the equation for voltage. S, by the way, is the voltage on the source. Same with anywhere I use S, it means source, it means the battery. And that's usually the total for the circuit, because usually that's the only power source. So it's going to be the total. So, Vs, and you could also use Vt for essentially the same meaning, is going to be equal to V1 plus V2, etc. When I say plus ... I just mean that if there are more loads, you just keep adding plus V3, plus V4, etc., etc., etc. So a series circuit has this really simple rule, which that the voltage or potential difference across the source is going to be equal to the sum of all the potential differences. That means that this potential difference that you would measure here is going to be the same as if you measure the voltage across here and across here, and add them up. And this is how series circuits work. Parallel circuits work in what we would call the opposite way, meaning that here, the voltage at the source is just equal to the voltage on each path. There's no adding involved here. Each path has the same voltage, and it's the voltage at the source. So whatever voltage this is, if it's 5 volts, the voltage here is also 5 volts, and so is it here. Okay. Now, parallel and series are opposites. Voltage and current are also kind of opposites. Let's take a look. The current rules for series are the same as the voltage rules for parallel. So current for series is just going to equal each other, always. That means that the current through the source is the same as the current through the first series resistor and the second series and the third series, etc., etc., etc. Parallel rules are the opposite, which makes them the same as the series voltage rules. That means here we're dealing with a sum. So there's this really nice kind of reciprocal thing here where these rules and these rules are the same, because series and parallel kind of work in opposite ways, and so their laws for voltage and current also work in opposite ways. So that's pretty simple to understand. Then resistance is just slightly more complicated, but not really. It's kind of a thing of its own. The rules for series resistance are very simple. Series resistance is just also sums of things. The total resistance, we could say RT, RS, whatever, is just going to be equaling the sum of all the resistances. And this is connected to an important concept which I'm going to get into called equivalent resistance. I'll explain that in a minute. In parallel, we have a much more complicated formula, but don't worry, it's not too bad. Here the resistance equals 1 over all of the resistances, but all under 1. So this is a little more complicated, but this is how it works for parallel resistances. And so these resistance rules are kind of separate from the voltage and current, but these are the 6 equations that are kind of integral to how electricity moves around circuits. There's 2 other equations that are not connected directly to these that I'm going to include. The first one is something called Ohm's law, which you may have heard of. And Ohm's law is this relationship between voltage, current, resistance. And it says that voltage equals current times resistance. You're going to see pretty well every rearrangement under the sun of this when you're solving for maybe current or maybe resistance or maybe voltage. Something that really helps me is this triangle, which I'll draw here. You might have seen this for other equations before. It's this pyramid with V on top and then I and R on the sides. And you can always use this same triangle to solve for voltage, for current, or for resistance. And here's how. If you need to solve for voltage, you just take V. Well, V is on a line by its own, so you write it alone. And then it just equals what's on the bottom. Well, it's just an I beside an R. Done. How about current? Well, current is here, and it's what you're solving for. And then you see the V is not beside the R, it's above the R. So you write it V over R. If you're trying to solve for resistance, you see R is alone, and the V is above the I. And these are the 3 different forms of Ohm's law that you'll use quite often. Ohm's law is very useful when you have current and resistance, you need to get voltage, or you have voltage and resistance, you need to get current, or any of those sorts of things. The other thing I'll talk about is an equation I'm just unofficially naming the power equation. And be careful, it's very easy to get the power equation confused with Ohm's law. The power equation is not the same thing as Ohm's law. It is P equals VI, and that just says that the power is equal to voltage times current. You're going to be dealing with power not a lot, but it will come up at some point, so it's important to know this equation. Just make sure you don't confuse P equals VI with V equals IR. They're kind of similar looking, and you might mess them up. So these are practically all the equations, and we talked about Kirchhoff's law and Ohm's law, that are practically needed in order to do what we would call circuit analysis. So we're going to move on to that, but before, I'm just going to cover one little additional topic, and this is the topic of something called equivalent resistance. And equivalent resistance is a pretty simple concept, but it sounds complicated. It's really not. I'm going to draw a little circuit to explain what I mean. Here. So this circuit is, complicated. It has, let me fix that. It has 4 resistors in a, arrangement with some series and some parallel, and, everything's going over the place. But here's the important concept of equivalent resistance. as long as all these things are resistors and there's nothing in the middle, which there isn't, and we really won't be dealing with anything other than resistors, all of these 4 resistors can be just taken out and replaced with a single resistor. And this circuit, which looks really complicated, becomes reduced down to this. Sorry. That circuit, which looks really complicated, becomes reduced down to this. This is much simpler, and this little resistor here is a representation of this entire mess. And how do we deal with equivalent resistance? Well, we use these equations that we know for resistance here, these series and parallel equations, and we break down the resistor until we get a single resistor that encompasses the same amount of resistance as all those other resistors. Equivalent resistance is a really useful concept. It doesn't work all the time, because, for instance, if you don't know one of these resistance values, it's not helpful. But it's extremely useful and a huge time saver because this circuit is a lot easier to deal with than this circuit. Okay. Finally, we are going to take a look at everyone's favorite topic, circuit analysis. Circuit analysis is a whole thing, and it gets very complicated when you have lots of different types of components in electronics. However, we don't have lots of different types of components. In fact, if you ignore voltmeters and ammeters, which are not really components, we essentially have 3 components that we could deal with. I'll draw them right here. These are the 3 things that can exist in a circuit, for our intents and purposes. This is a battery, and all we need to know about the battery is that it is the source of the electricity. The battery has a voltage and a current associated with it, and there's probably a total resistance as well. This is a wire. And the only important thing to know about a wire is that, for our intents and purposes, again, simplifying, but that's what we do, the resistance across the wire is 0. There is no resistance. This means it literally does not factor into any calculations ever. You can literally ignore its presence. The only reason wires are important is what they're connecting to what. For our intents and purposes, there is no difference between this circuit, between this circuit, which has a long wire, and if I drew the circuit like this. Doesn't make a difference. The wire does not factor in. Finally, we have resistors. And this resistor, which we might also call a load, which is a more general term for just a thing that has resistance, is really a stand-in for all sorts of things. It could stand in for lamps or motors or, LEDs. Doesn't really matter. For our intents and purposes, we just deal with these loads that have fixed resistances. So this is going to have a specific R that we're going to know. It's going to equal some value. Sometimes you'll have to find that, sometimes it'll be given to you, but that's all a resistor is. It's just a thing that has resistance. So really, all circuits, and I literally mean all circuits, are made out of these pretty straightforward concepts. And when they combine, things might get a little more complicated. So we're going to do maybe a couple examples. I'm definitely going to do at least one. So let's start with this circuit here. I do want to draw this kind of nice, so let's take a look. Okay. So this circuit that I'm drawing here is an example of a circuit which has multiple components to it. That means there is a component of it being series and a component of it being parallel. And we're going to look at how this works. Now, the first thing to notice is this circuit. We know the voltage of the source. This right here is the voltage of the source, or the total voltage. And we know the resistance of each of these resistors. I am arbitrarily numbering these 1, 2, and 3 based on just how I feel. And we're going to look at these things, and we are going to figure out the total current. The thing with the question mark is what we're looking for in all cases. Sometimes you'll have things which ask for a chart with all the values. Those are annoying, but they do happen. But most often, you're probably going to be dealing with question marks that it wants you to fill. So, how do we approach this circuit? We don't actually have any tools for dealing with this type of circuit. This is a kind of series, kind of parallel-ish circuit. And we can't just deal with that. So we need to reduce this circuit down to a circuit that we do know how to deal with it. We need to subdivide the circuit. It's similar to how in math, if we have complex equations that we have no clue how to solve, we typically start by doing things like factoring, etc., that simplify the equation down to the point where we know what to do. Same thing here. We're going to move stuff around, simplify things until we know what to do. And the first way to approach this is using that technique we talked about of equivalent resistance, which is useful here because we do know all the resistors. That means we can strive to reduce this circuit to that desired circuit we all love, which is one resistor on a battery. We're going to try and get from here to here. And in order to do this is a little bit of work, but not too much. So let's just take a look. The first thing we're going to do is tackle these two resistors here. These two resistors, isolated on their own, ignoring everything else, are a parallel circuit. You can tell. There's two paths, goes one path, two paths, has a junction. It's a parallel circuit. We are just going to take those two resistors and combine them, smush them together. Now, I like to use names that make a lot of sense, so if we're dealing with R2 and R3, the smushed together resistor is going to be called R23. And our smushed together resistor R23 is going to have the resistance of these two resistors together in parallel. Now, if we go look over at our formula for parallel circuit resistance, we see it's the 1 over R plus 1 over R2, etc., etc., and so on. And so we're going to go ahead right away and say, well, this is going to equal 1 over R2 plus 1 over R3. Because these are the two things that are in parallel. We have an R2 and an R3. And so R23 is those two things put in parallel with each other. And, you could then sub in the values and you're going to get 1 over 5 plus 1 over 5. And trust me on this, it equals 2.5. 2.5 ohms. And this is the resistor value of R23. So now I'm going to draw the intermediate step. Now you don't actually have to do this when you're solving, but I just want to show you what we've reduced the original circuit down to. We've simplified it one step. We now have a circuit which looks like this. This circuit still has the total voltage, which is 6 volts. It still has an R1, which is 5 ohms, And now it has replaced these two resistors with one resistor, R23, which is 2.5 ohms. And this is our next step. So here, I'm going to label this. This was step 1. This is step 2. From step 2, we are in a better place now. We do know what to do with this circuit. This is a simple series circuit. And remember, we're trying to get to the ultimate stage of just one resistor. So these are two resistors in series. It makes sense to reduce them down. And again, if you have R1 and R23, you can merge them into R123. And we're going to use the series equation for resistance, which again, if we slide over here, was simply just adding R1 plus R2 together. And so R123 is going to be R1 plus R23, which is really simple. And that's going to be 5 plus 2.5. And it's going to equal 7.5 ohms. Problem solved. We now have this value for R123, and we can reduce our circuit even further. Here's the new step. We now have a circuit which looks like our end goal that we really wanted, where we have a single voltage, and we know it's 6 volts, and this R123, which is equal to 7.5 ohms. And when you have one resistor, this is also RT, the total resistance. And that's the same thing as 1, 2, 3, because it's the only thing there, it's the total. From here, the thing we were actually trying to find originally is the total current. That was the thing with the question mark. And to get this, we know voltage, we know resistance. There's no possible way to simplify this circuit further. We need to find current. We know how to do this. It's our friend Ohm's law. Ohm's law, but rearranged for current. I like my triangle. Voltage on top, current here, resistance here. We're solving for current, so we go over here, and we say, okay, we have an I alone, and it equals a V over an R. And given I equals V over R, we can then, these are all the T's because they're the totals in the circuit, we can do 6 volts over 7.5 ohms and get our answer, which is 0.8 amps. There we go. It's also important to keep significant digits in mind for these questions, which even I forget often. For instance, all of these values in the original question had just one significant digit, and so we also would want to keep this answer to just 0.8, which would be one significant digit of precision. And that's our final answer. Now, if we tried to solve that final answer from the initial thing, it would be virtually impossible, because there's no way to analyze such a complex circuit straight off. What you do, though, is you simplify. You break into parts that you do know what to do with, you do something with that part, and you come back and say, okay, how have I simplified? Now, when you're actually solving this question, I don't encourage you to actually go ahead and divide each part and rewrite what the new part, although feel free to do it if it helps you. That's great, especially in homework. When you need to do things a little faster, you can eliminate these drawings and just jump to these calculations in between. And this will come with time as you get better at it. And then you'll be able to get your answers for these kinds of equivalent circuits. Alright, so I did want to do one more, and I'm going to do maybe a slightly more complicated one-ish. We're going to tackle one which has an unknown resistance, because they're slightly more annoying. So let's take a look at this circuit here. This time, the battery is going to be at the bottom. So we have this battery here, a resistor here, and 2 resistors at the top. So this time, we're given some limited information, and again, it's all about what information you're given that always matters. So I'm going to number these resistors. Here's R1, R2, and R3. R2 is 3200 ohms. R3, we don't know. We know R1 is 3800 ohms. Then we're given the total current, IT, 58 milliamps. And we're given the voltage on R1, 120 volts. If we take a look at this, this looks immediately more complex, but we're going to apply the same principles as before. One small thing I'm going to do before even starting is convert everything to base units. Milliamps needs to be converted to normal amps, which is just 0.058 amps. That's because a milliamp is 1,000th of an amp. Okay. Now we are going to go ahead and kind of look at this critically in the hopes of beginning to analyze what on earth is going on. The first thing we can notice is we have things in parallel. If you ignore these 2 resistors, again, in the spirit of simplifying, and just combine them into a kind of hybrid resistor that's R23, we're not even going to look for this value yet because we couldn't find it. But let's just look at this circuit. If we ignore the presence of those 2 resistors and we just have R23 up here and an R1 here and your thing, this is a simple parallel circuit. It's kind of rotated on its side, but it's a simple parallel circuit. One thing we can know about this is how voltages work in parallel circuits. If we jump back over to our equations, one way voltages work in parallel circuits is that all the voltages on each branch equal each other. You have V1 equals V2 equals etc., etc., etc. So over here, we do know one branch's voltage. It tells us 120 volts. And so we can actually come to the conclusion that since V1 equals 120 volts, the total voltage is also going to equal it. So is V1, so is V23, and they're all going to equal 120 volts because every branch of a parallel circuit equals 120 volts. This is a good tip. If there's something like this, which you can kind of see before even starting, this is always super helpful insight. It's always good to get the total values if you can. If you can find total voltage or total resistance or total current, that tends to help you a little bit in the question. For instance, we can also look at total resistance. We have total current and total voltage. We can look at total resistance using Ohm's law again, which is just Vt over It. That's going to be 120 volts over 0.058 amps, which is going to equal 2069 ohms. Perfect. That is RT. We now have IT, VT, and RT. We're in a good place. The next thing we need to look at is, okay, we have this R23. We can't solve for R3 right away because we don't have enough information, but we can at least approach trying to solve R23. Well, in order to figure that out, we are going to need to take into account, again, the fact that we're in a simple parallel circuit here. So R23 and R1 have this resistance relationship from our formulas over here. Remember these guys? It's the one with the 1 over 1 over R1 plus 1 over R2 and so on. So let's apply it. We know that RT is going to equal 1 over R1. It's going to equal 1 over R1 plus 1 over R23. And we can basically simplify this down a bit, and we are basically trying to solve for R23. There's a couple steps here, just take my word for it because I don't want to go through all of them, that we can rearrange it to a form that if we sub in the value for R23, we'll get R23 equals 1 over RT minus 1 over R1. Then if we put in the values, we get 1 over 2069, remember we found that over there, minus 1 over 3800, which is the value of R1, and we can get 4542 ohms. This is the value of R23. And R23 is going to be helpful because of a basic fact. R23, we can now look into it. What is R23 really? And we're going to isolate a different part of the circuit now. Before we were isolating this and ignoring the two resistors. Now we're going to isolate this. That's R23 right there. And it's just two resistors in series. Remember our series equations? Right over here. The equations for series is simply adding the resistances together. So we can come to the conclusion about R23. The R23 is just going to be R2 plus R3. Very simple. And we can rearrange this for R3, which is, remember, the value we're actually trying to find out here, by going R3 equals R23 minus R2. Sub in the values again, 4542 and 3200. That equals 1342 ohms. And because, of course, significant digits are all a thing, if we look at significant digits, the smallest number we see here is 2 significant digits. And so this number becomes 1300 ohms. And that's the value of R3. So this question was arguably more complicated than the last one. There were more steps of calculation and was a little more complicated to reason about. But the steps that we followed, the process we used was exactly the same. We search for things that are so complicated. When we have them, we reduce. We use equivalent resistance. We started by saying, oh, well, this thing is really complicated. But there's a parallel circuit here, just with some extra complexity. So we remove the complexity, and we go over to here, and we're like, oh, it's just a parallel circuit. Now I can do calculations on this parallel circuit until I have enough information to go back and be like, well, what's inside this? And we peel back a layer. And here we find that the parallel circuit had a series circuit inside of it, and now we can do calculations on that series circuit. And this is basically the whole point and the whole philosophy of circuit analysis. Basically, think of circuit analysis like an onion. Yeah, I know, that's an interesting analogy. But it's all about layers. The whole onion, the whole circuit, looks very complicated. But if you peel back layer by layer by layer, each layer is a rather simple circuit that you can analyze and then plug in new values and keep moving on. It takes lots of practice, definitely does, and lots of getting good at figuring out what you need and what you see. So definitely do some circuit analysis questions. Google resistor circuit analysis questions to find questions that are circuit analysis with just resistors, and you'll find even more practice problems. And you can check these out and figure out what's happening in them and start to understand more about what's going on in these circuits. Because at the end of the day, that's what circuit analysis is. It's just all about finding out what is happening in these circuits. Whew. This was a long video. There was a lot we covered here. We looked at Kirchhoff's current and voltage laws, series and parallel circuits and their formulas, equivalent resistance, Ohm's law, the power equation, and then we went through some examples of circuit analysis. Hopefully this has served as a comprehensive sort of video detailing all about electricity. In a video soon, I will talk about some of the concepts in magnetism, which is the other half of the unit on electromagnetism. Electricity, then magnetism. Hopefully this was helpful to you. Thanks for watching.